Hello, today I want to show you how power system analysis and load flow analysis is performed. This will be the toughest lecture I ever had. Power grids are three-phase systems which are complex to calculate and thus require a lot of CPU time. For load flow calculations, however, we can assume that the loads are symmetrical and therefore we can use a single-phase model. Load flow analysis is one of the most fundamental tools for the design and the operation of power grids. For example, it helps to check if there is enough transmission capacity to perform the intended power exchange. And the second thing is that it allows to check if the voltages at any point in the grid stay within the specified tolerances. So normally it's plus minus 5% of the nominal voltage. This is now the most basic example of a load flow calculation. What you can see here is a power source. This is a voltage source. The source has a 200 kV peak. This is the blue curve you can see here. So it corresponds to a three-phase 245 kV system, but just one phase representation. Then I have a bus bar. The bus bar is normally a substation. We call it also a node in the network. And here directly at the same bus you have a load. In this case the load is just an ohmic resistor. And what you can see now is that the power source supplies power, so as soon as a source is supplying power, it depends on how you count the system. I have defined that then the power is counted negative, and if an element receives power, the power is counted positive. If I replace my ohmic resistor by a reactor, you can see that now the power is oscillating back and forth between the source and the reactor. And here I have now a mix resistor and a reactor. And you can see that also the power is now mixed. There is an oscillation back and forth. This is due to the reactor, but there is also some resistive power, and this is basically why you have an unsymmetrical distribution of a positive and negative power in both in the source and in the load. A very important feature for power flow calculation is that I can vary the phase angle of this power source. As long as I'm very simple, like here, it doesn't influence anything, but just for demonstration purpose you can see that I can vary my phase angle between plus and minus 90 degrees. I have now increased the complexity of my schema a little bit, so I have introduced a power line. This is a 100 kilometer line, again on 245 kilovolt three-phase, and here I have another power source. What you can see now is that the phase angle of both power sources, so the voltage curves are on each other. That means there is no phase angle difference between this voltage source and this voltage source, and that means also that this power source here is not contributing to the power of this load. So all the power this load needs now with this phase angle difference between here and here comes from this source. But maybe I would like to have a part of the power coming from this source, because it may very well be that here I would not have enough power, or that the power which I would get from here is cheaper. For example, here it could be solar or wind, and here I would have nuclear. So maybe I want to share the power in order to reduce the cost. But what do I have to do then in order to get a little bit power from this source, which for the moment is zero? What I have to do then is to start to increase the phase angle between this source and this source. So this is what I'm doing now. You see, I increase the phase angle, and from the moment I do that, power is supplied from this source as well. So the load here is sharing the power between this source and this source. The more I increase the phase angle, the more power I get from this. And this is exactly how you control the power sharing between different sources in a network. So how do you establish now the phase angle difference between these two sources, which you can see here? Here I have the curve from the source on the left, and here I have the curve from the source to the right. So this phase angle difference, this is what creates the power sharing. How do I establish this phase angle difference? By the torque. So as soon as I start to increase the torque, I push more power, then I increase the phase angle, and then automatically I get more real power from this source to the real power needed somewhere. So this applies really for real power. The torque supplies real power. Please note that there seems to be also something like a reactive power in the system here. How can that be? Because I have only a real load. So the reactive power is coming from this line here. So the line has a reactance, and therefore you will always see in such a system also somewhere reactive power. So this is what you can see here. Power is oscillating back and forth a little bit. It's not so much, but if you have longer lines, this starts to be much more pronounced than what you see here. Here we have now the time domain, and we can now go and look at the phasor domain. So I'm just looking at the phasor now. You see now the phasor domain. You see the voltage sources are represented as phasors. So this is this phasor, this is this voltage source, and you can see that there is a phase angle in between. This is what we have seen already before. You see the real power stays on the real axis, and the imaginary power or the reactive power stays on the imaginary axis here. So this is then the source power here, and they both share the reactive power consumed by the line. This is why you have some imaginary, and the part of the reactive power is also exchanged between the two sources. You can see that this voltage source is now leading this one. And if this voltage source or this generator is leading this other generator here, I can see that the power is flowing from here to here, and this is represented by this arrow on the line. If I would have a source where the voltage would be lagging, you would see that the arrow is changing direction, and you always see how much power is flowing through the line. So this is already a little power flow analysis, what we are doing now here. And I will show you how you do that really for more complex systems right afterwards. But you can see here what happens in the system. I can also go back to the time domain and then do the same thing. So you can see how the power is shifted from positive to negative. If the power would be positive, that would mean that this generator here would act as a motor. Gradually increase now the complexity of my network. Here, the first step, I have added another line in parallel. So I have now two lines in parallel, and I share the power for this load here between these two sources. You can see that they share the power. They equally contribute to the load here. But what happens now if I open one of the two lines? You can see now that I get much less power from this side than from this side. Because if I have only half of the transmission lines, of course also only round about half of the power can be transported from here to here. What would I have to do now if I lose one of the lines and still want to transmit the same amount of power as before? What do I would have to increase the phase angle. When it was closed, it was around about 7 degrees to share. You see 7 degrees. And if I open it and still want to have the same sharing of the power, I would have to increase it from 7 to around about 10 degrees. Very sensitive with this relatively short line. I have now slightly increased the complexity of my network. I have introduced a third bus here with a resistance. I have the same resistance like here, and therefore I would expect that I also get the same load, the same power at the resistance. But this is not the case. You see I have less power here, and if I'm looking exactly at why this is, I see that I have less voltage at this node here. And I need to compensate this voltage. First, let's have a look at how much less this voltage is. In order to measure the voltage, I connect a probe in parallel to this resistance, and I set the probe at the target voltage at this point, which is a 200 kilovolt peak. And now I can measure the voltage at this point. You see, I have only 96% of the nominal voltage, and I need now to increase the voltage at this point. I have two options to do that. I can either increase the voltage at this source here. Let's do that to see what happens. So I need to increase it by around about 20%. So I go to 220 kilovolts peak. Let's see what happens now. Yes, you see now I'm close to 100%. And of the voltage, of the nominal voltage. But the problem is that now at this point I have a too high voltage. So I'm far above nominal here, and that would not be allowed. So the other option I have is that I compensate the reactive power at this point, and I do that by introducing a capacitor. Let's see how this is done. I have now added a capacitor in parallel to the load here. And with the capacitor, I intend to compensate the voltage drop by these line reactances. And in order to do so, I need to adjust the capacitor until I get 100% nominal voltage at this load. And you see how this is done, and this is where we are. And now I have achieved what I wanted to have. I have the same nominal voltage at this load here compared to this one, and I have everywhere the same nominal voltage. And the only thing which is now different, I can continue to vary the phase angle between the two sources against each other, so that I can distribute the power from one source to the other depending on what I want to achieve. If I need to have more power from this source here because it may be cheaper, then I just increase the phase angle, and then more power is coming from here. And the other way around, if I reduce the phase angle, I get more power from the other source on the other side. So you see how this is done now. So this is now a perfect example of load flow calculation, but in a very simple case. Of course, I can also go to the phasor model, and here you see the phases of the individual sources, and you see the voltage at this point. And you also see in the lines how much power is flowing from one bus to the other one. And of course, if I adjust the phase angles, you can see that I change the power flow through the whole model. In this lecture, I want to show you in details how such a load flow analysis is performed mathematically. Here on this picture, you see a variation of load flow pattern during the day. And for our load flow calculation, we assume that for each and every point in time, the network status can be considered static because the flow is varying relatively slowly during the day. So the first assumption is that we can go for static calculations for each and every point in time separately. And the second assumption we do make is that we have symmetrical loads. So we consider one phase only. So a load flow analysis is performed in 4 steps. The first step is that we set up the network model. The second step is that we set up the node admittance matrix. The third one is that we define the target power. For each and every generator, we define how much generation we want to perform at this point. And then step number 4 is that we will then optimize the voltages and the phase angles at each one of the buses so that of the network model, so that the intended power supply scheme can be met and none of the components exceeds the tolerances. So for example, not too much current, not too high voltage, and that the power flow is not exceeding the limits, for example, of transmission lines or cable. So let's go now to step number 1. We set up the model of the network. Here is the simple network. So we have 5 buses. It's bus number 1, bus number 2, bus number 3, 4, and 5. Then we have transmission lines. We have 6 transmission lines. Between bus number 1 and 2 we have L1. Between bus number 1 and bus number 3 we have L2. And the other ones you can see yourself. These are the transmission lines. Then we have generators. These are symbols for generators. And then we have loads. The arrows are symbols for loads only. So for each one of the generators, then we fix the target real power and the target reactive power. We do that for all the generators, and we do the same thing for the load. The target load power, real power, and reactive power. I told you already that the buses stand for substations. In the first step, we assume now that we know all the power sources at all the buses, and we know all the loads at the buses. And knowing that, we want to capture now the load flow through all the components, in this case primarily lines. And we want to calculate the voltages and the phase angle of these voltages at all the nodes, at all the buses, under all possible load conditions. This enables to secure that none of the components is overloaded, and the system can be operated securely and stably under all conditions. We want to have a closer look now at one of these buses. So in one of the buses we are injecting power by means of a source, and we are kind of removing power by means of a load. The rest is coming or going into lines. So the sum of the power injected in the bus number K is the real power Pk and the reactive power Qk. The real power Pk is equal to the Pgk, which is the generation. So the generation is injecting real power Gk and minus the real power Lk for the load. And the same applies for the reactive power Qk. The full reactive power injected in the node is Qk is equal to the sum of Qgk, which is the generation, minus Q load K. Therefore, we can now simplify a little bit our injected power into the node. You see that instead of having a separate injection for the generation and a separate injection for the load, we have now one common injection, Pk and Qk, for the bus number K. In order to keep now the balance between the injected power at the bus number K and the power flowing to the lines, we have the following equation. The sum of the injected power, real power Pk, is equal to the real power flowing to the line, Pki, which is this one, plus Pkj, which is this one, plus Pkm, which is this one. The same applies also for the reactive power. The sum of the reactive power injected in bus number K is equal to the sum of the reactive power flowing to the lines, which is the Qki, which is this one, plus Qkj, this one, and Qkm, this one. What we want to know now for this bus number K is the voltage at the bus and the phase angle K at this very bus. Just remember that this representation here is just another kind of writing for a vector Vk underlined, which is the same as Vk absolute times e to the power of j phi k, which is then Vk times cosine phi k plus j Vk sinus phi k. So this is a complex number. So coming back to our main circuit, we see now that we have all the buses, and at each one of the buses you have injected power, a real power and a reactive power, and now we have also the voltage vector which we are looking for. For the lines we will use a simplified model, so we will have the series reactance and the series conductor resistance, and on both line ends we just take half of the segment capacitance and half of the segment conductance, and we will basically present it as follows. So this part is equal to this admittance here, this part is equal to this admittance here, and here we have these two elements. Now we are going to perform step number 2. We want to set up the admittance matrix, but first we have to know what is exactly the admittance matrix. So here we have this very simple network. The network has n buses. In this case, n is equal to 5. So we have bus number 1, bus number 2, 3, 4, 5. Then at each of the buses we have a voltage. Voltage is a complex value, therefore it is underlined here still. So we have at bus number 1 we have voltage number 1, voltage number 2, 3, 4, 5. Then since we have voltages at each one of the buses, we inject a current I1 at bus number 1, current I2, 3, 4, 5. And this is exactly now what is represented in this current admittance matrix. On the left side of the matrix I have the currents, and the currents are a function of the voltages, and here we have this admittance matrix. So I1 is equal to Y11 times voltage at bus 1 plus Y12 times voltage at bus 2 plus and so on plus Y1n times voltage at bus n. So this is how this matrix is set up. You may have noticed that sometimes I call the bus nodes, so node and bus is the same thing for me. Let's now set up the admittance matrix. In order to be simple enough, I've chosen to reduce the number of nodes to 3. So I have bus number 1, 2 and 3, and between the buses I have lines. So line 1, 2 between bus 1 and 2, line 2, 3 between bus 2 and 3, and so on. And at bus 1 I inject the real power P1 and the reactive power Q1. Bus 2 I inject the real power P2 and reactive power Q2, and so on. For the lines I introduce now the line model which I have been showing just before. So for each one of the lines you have a series admittance for the line. This is, for example, this Y12. Then you have on both sides of the line you have the shunt admittance. On the side of the node number 1 you have Y120, and on the side of the node 2 you have Y210. Let's start to write the equations for the current. So be aware that the current, the voltages and the impedances are complex, but I do not underline it here for simplicity reasons. So the current I1, this is the current which is injected into node 1, is equal to the current IL12 plus IL13. I can substitute the current IL12, this is this current, by the sum of the current I120 plus I12. I can also substitute the current IL13 by the sum of the current I130 plus I13. So these two currents. Therefore, the current I1 is now equal to the current I120 plus I12 plus I13 plus I130. This is when the bus voltages come into play. So I put now V1 on bus number 1, V2 on bus number 2, and V3 on bus number 3. And I can start to substitute all the currents which are on the right side of the equation by their respective voltages. I can do this like this. So the I12 is equal to, this is this current here, I12 is equal to the difference in voltage across this length admittance times the length admittance. So I1 is V1 minus V2 times Y12 plus V1 times Y120. So V1 times Y120 is equal to this current here, plus V1 minus V3 times Y13 plus V1 times Y130. So now I managed to substitute the right side of the equation by voltages times the admittances. For the other two nodes, node 2 and node 3, or bus 2 and bus 3, we apply the same procedure, and as a result we get the following equations for the node currents. So this first row was the equation we already analyzed just before. We do now exactly the same for bus 2 and bus 3. So bus 2 is equal to V2 minus V1 times Y12 plus V2 times Y210 plus V2 minus V3 times Y23, so V2 minus V3 times Y23 plus V2 times Y230. For the I3, current on bus number 3, we get again the same pairs of equations. I will not repeat it. It's quite obvious now what has to be done. So we have now got the equations. The next step is that we are removing the parentheses. So here there is no parenthesis anymore, so this is exactly the same expression like this one, but just we removed the parentheses, and we do that for all the 3 equations. The next step is now that we regroup the voltages, so all the admittances which are connected to the same voltage are put in parentheses, so I have only one voltage anymore, and all the admittances are within brackets. And I do that again for all the equations. So the last step is that I rewrite all these equations in matrix format, and we got what we wanted, our admittance matrix. Here we have the matrix notation in a more generic format. So you can see that this matrix can generically be represented by such a matrix. So we have a 3 times 3 matrix, and also the generic notation of n times n matrix would be like this. In such an admittance matrix, we have 2 types of elements. We have the diagonal elements. These are the ones which are in the middle here, 1, 1, 2, 2, 3, 3. And then we have the side elements. And in the setting up such a matrix is now very easy. It's always the same principle. In the diagonal elements, you have always a sum of all the admittances which are connected to the bus. So the admittance Y11 is equal to the sum of all the elements which are touching bus 1. So this is Y120, Y130 plus the length elements. This is what you see here. And the side elements are always minus the length admittances of the lines. So Y12, Y13, and important minus. So this minus sign is very important. And you can always see that Y21 is normally equal to Y12. There are very few exceptions. In this very simple case, all the elements of the matrix are non-zero, but if you would have now a bus which is not always connected to all the other buses, like this is the case here, then it can well be that some of the elements would be equal to 0. What we have now achieved with this admittance matrix is that for each and every voltage at all the buses, I know the corresponding injected current at the same buses. So what you see on the graph here is, first of all, the blue voltage phasors. This is what you see here. So for example, this one is the blue voltage phasor for this voltage source, for this generation. And the same applies for the other ones. For the resistances, you also see the corresponding blue phasors, including the phase angle. And the green phasors are then the corresponding currents, which are injected then as a function of the voltage at this bus. So the currents are a function of the voltage. So currents equals admittance matrix times the voltage vectors. This is what we have now achieved. And of course, I have also for all the lines, I have a corresponding current phasor. And this will allow me later on to determine whether my line is overloaded or not. So you see here the green phasor, what you see here, and here is the same green phasor for another line, and I have the same information for all the lines. What I also get, since I have now the voltages at both ends of the lines and the currents going through the line, I know also the corresponding power which is fed through the line. Since I know the currents, I know the voltages and the phase angles at all the buses, I also know the power. So you see that for each and every voltage and current, I know all the powers in the whole system. The only thing which I am missing now is a possibility to go the other way around. I would like to tell to the system that I want to have so much power from this source, so much power from this source, and so much power from this source. Please, dear system, adjust the voltage phases accordingly so that I get at the end of the day the right distribution of the power for the sources but also for the loads. This is something I'm missing, and in order to get there I need to go one further step. If I want, I can also highlight the power. This is the red phasors in my phasor diagram. The real power of the red arrow is on the real axis, whereas the reactive power is on the y-axis. This is this imaginary axis. So real power and reactive power. So what we have got so far for a given network, we have calculated the admittance matrix, and the admittance matrix shows the relation between the voltage at the buses and the currents through these buses. So if the voltage is known for all the buses, the current is known, and since the voltage and the current is known, we also know the apparent power, this S, which is equal to voltage times the conjugate complex of the current. So the third step now is that we want to define the target power at the buses. We want to inject the amount of power at all the buses so that the load gets the power specified. We want to distribute the power needs amongst the generators so that we can produce it at lowest possible cost. So it's a dispatching topic. And we want to satisfy the reactive power requirements. And this problem can be solved iteratively only. So what I will do now is that for all the buses, bus number 1, bus number 2, 3, 4 and 5, I will define the target power. This is the power I want to supply to this bus in order that all the buses will at the end of the day really get the power they need. So I have decided that for bus number 1 I will want to inject 190 megawatt by the generator which I have connected to this bus. I do not want to inject reactive power. The bus number 2 will get a generator which supplies 135 megawatt real power. Also here I do not want to supply some reactive power. The bus number 3 will consume 172 megawatt because it is a resistance and the resistance consumes real power. The same thing applies for bus number 4, where I have 120 ohm resistance, and these ones will consume 162 megawatt. By the way, this is a 245 kV system, which corresponds, it's 3-phase, which corresponds to a single-phase peak voltage of 200 kilovolts. So I assume it is peak voltage. And in order to compensate the reactive power, I foresee here to inject 100 megawatt. I do that by means of a capacitor. And here, this bus here is an exception. One of the buses in the system needs to be a slack bus. The slack bus does not define power. The slack bus just defines a voltage phasor, and the voltage phasor normally is a reference phasor, and in this case I have chosen to have a 200 kV reference phasor with 0 phase angle. And this one will stay constant during the whole iteration process. And the slack bus in return will consume or deliver the power which is needed by the system, which is not already delivered by the other sources. So if I have, for example, a deficiency in reactive power, these slack buses will take the deficiency and will supply the reactive power which is not supplied by the other sources already. For example, if I have a too small capacitor here, the reactive power will be supplied by this slack bus, because here I do not define neither real power nor reactive power. So this is free floating and will be defined during the iteration process automatically. By the way, the power of bus number 1 is of course the sum of the power delivered by the generator minus the power directly consumed by the resistance here, by the load here. This is the model I apply for the lines. So I have different line lengths. And here I have the capacitor, the inductivity, and the resistance per kilometer. I'm working with a 50 Hertz system. So there are four possible iteration methods which are well known. The first one is the try and error. I would not recommend. You will take days until you are there. Then there is a very useful one. This is this Gauss-Seidel iteration. This is what I will demonstrate and explain how it works. Then there is another try and error, but a little bit more sophisticated, which is easy and where you can find the result quickly. This is my software, which I want to propose later on. It will be demonstrated. And then the fourth one is the Newton-Raphson iteration. This is optimal for very large networks. It's pretty complicated to set up the equations, but it works, and there I refer to the literature. I'm going to explain now the Gauss-Seidel iteration. There are two basic equations. The first one is the one we have been working with so far. I of the row k is equal to the sum of ykn times vn. This is basically what you see here. So y21 times v1 plus y22 times v2 and so on. So if k is 2, this is basically the row number you would choose. And then the second equation is the apparent power is equal to real power plus J times reactive power, and this is equal to the voltage time the conjugate complex of the current. I can change this a little bit. If I want to have the conjugate complex of the voltage and eliminate the IK, then I need to change the conjugate complex. Instead of having the current conjugate complex, I take voltage conjugate complex, and then instead of having P plus JQ, I have P minus JQ. So then I have conjugate complex on both sides, so then I can eliminate this IK. So if I have eliminated the IK, I have on one side of the equation, I have this term here, and on the other side of the equation, I would then have this term here. This is what you can see here. So I prepare now this equation here to make it fit for the Gauss-Seidel. So for that purpose, I put everything to the left side, of course with the minus side, except one term, which is this diagonal matrix element YKK times the voltage which is corresponding to this diagonal element. So YKK times VK is staying on the right side for the time being, and all the rest goes to the left, therefore this minus side here. And then I divide this whole term. Now I have kind of changed the sides. I take this one to the left side and this whole term to the right side, and I divide this whole term by YKK. And then the only remaining term on the left side is the voltage of bus K. And this is the equation I will need from now on for the Gauss-Seidel. Again, this is the same equation here. I have now grouped the terms before the diagonal under one summation and the terms after diagonal under the other summation. And the diagonal part is extracted as we have learned before. So we have the row K, VK, and here we have YKK. The iteration works now as follows. For each iteration cycle, I start with row number 1. So here I will get the result of this formula here. Here I have the old voltage values, and based on this formula for the row number 1, I get the new voltage value. Then the second part of the iteration, I'd take this new voltage value here and insert it here into this term. So you see here the left side of the diagonal always gets the new value which has been calculated here, always here, whereas the right side of the diagonal still has the old values of the voltage. And so I continue like this. Then we have row number 3, again the same principle. I just take these two new values and insert it on the left side of the diagonal, whereas the right side of the diagonal still have the old values of the voltage. And I do that for the whole cycle until I reach the end of the cycle. And at the end of the cycle, you see that I have nothing anymore on the right side of the diagonal. The diagonal itself is what I get here. So this is how it works. This is the iteration cycle, and the starting point, this is important now. For the starting point, I am using the terms of the voltage which I have assumed at the beginning, and I have assumed that at the beginning of the iteration all the voltages at all the buses are equal to the voltages at the one slack bus. So for example, in my case now, if I have defined that at the slack bus I have a peak voltage of 200 kilovolts with 0 phase angle, I take the same voltage for all the buses and put it here, insert it here for the first iteration cycle. And at the end of the iteration cycle here, I will replace the old values which I had in the previous cycle by the new values, and now the new values are the old values, and I start from scratch. This is how it works. If I check my iteration, I will notice that at each iteration cycle, the difference between the new values of V and the old values of V will get smaller and smaller. Here is now a demo. I have used now this network, which I was talking about all the time before. The first thing I had to do is that I developed this not admittance matrix. This was what you can see here. I mean, this alone is already quite an exercise. The second thing is that I have defined the values of the apparent power. This is what you can see here. So you see that this is the slack bus. There the initial values are equal 0. And on the left side here I have all the values for the voltages at all the buses. And you see that I have just taken the values of the slack bus, which is 200 kilovolts with 0 phase angle, and I have used this one value as initial value for all the buses. So I go now into the first iteration cycle. So you see now that I have already quite a substantial change of the values. The program also calculates the momentary values for the apparent power. You see this is the real power and this is the reactive power. And you see that at each and every iteration cycle this change. The changes are relatively large at the beginning of the iteration. And as I progress with my iteration, you see that the difference gets smaller and smaller and smaller. I have now around about, let's say, 20 iteration cycles. I continue like this, and after a while you will notice that the changes are starting to be minuscule, and that I am approaching now the target values I had at the beginning. You see that for the power at bus 1 I had a target value of 100 megawatt real power. Here I have now 100 megawatt real power. I still have something on the reactive power, so this will continue to get smaller and smaller. For bus number 2, this is the value you can see here, and so on. And for the slack bus, you see that I do not have any more 0, but the slack bus now takes the difference between what I have on the other buses plus what my system needs. So you see that on the other buses I lack of 160 megawatt real power. So if you would build the sum of the real powers here plus the real power which is consumed, but plus all the losses which I have in the lines, then I would miss 160 megawatt. And this 160 megawatt real power is now delivered by the slack bus. And on the left side you see the voltages. This was the initial voltage in red, and now I have a little bit more. And what is also important to notice is that the phase angles have changed. So I have now suddenly much more on the reactive voltage side than I had at the beginning. At the beginning I had 0, and now I have a phase angle which I did not have at the beginning. And I can continue for a while until I have basically really reached what I wanted initially. I'm already very close, and you see that basically the reactive power which I still have here on these buses is basically close to 0. So yeah, now I could stop my iteration cycle, and that would be the result at the end of the day. So here are the voltages I was looking for, starting from my assumption at the beginning, and now I have achieved what I wanted. And with these voltages, I now really get the target power at each one of the bus. At the end of this lecture, I would like to make a demonstration where you can see in a more hands-on manner how you can achieve a very similar result as we have shown before. So this is now my program I'm proposing to you to learn. You see the network. The only thing which has changed compared to what I've shown before is that I have introduced here and here a transformer so that I can measure the sum of the power coming from the generator and the load. So here I get the sum, the same thing is here. Here is my slack bus. And what I have done now, the slack bus is just a voltage source. You see, the voltage source has a peak of 200 kilovolts, a 50 Hertz frequency, nothing else. However, for the generators, everything outside my slack bus is now really working as a generator, and these generators have a power. Have a maximum power of 400 megawatt, both of them. You see, this one is the same thing. It is not only a voltage source, it is really a generator. And the point with this approach is that in order to get power from these sources here, I have to increase the torque. By the way, I have to also add the droop here, otherwise it's oscillating. So I want to have a droop. And if I'm running now this one, I see that if I want to increase now the power, now all the power is basically coming from the slack bus, but I would like to, the slack bus is too expensive maybe, and I would like to get more power from my own generation. What I'm doing now to increase the power of my own generation, this is the clue, I increase the torque. So just by increasing the torque, I get more power, and you see I get now more power from this bus here, and at the same time, the slack bus power is reduced gradually. So I can further increase the power, and I want also to get more power from this other generation point. So, and you see that by doing so, the power, the real power which I'm getting from my slack bus is gradually decreasing. Now I continue to increase the torque. And just by increasing this torque, you see, I'm already now at a very small contribution of the real power from the slack bus. And just by increasing the torque here, I kind of automatically get the setup which I want. Now I have zero real power from the slack bus, and I get all the power I need from the system from these two sources here. I can redistribute slightly the power between these two sources. So you see, so here it is a manual exercise, and it is not, let's say, as precise as what I have shown with the Gauss-Seidel, but here you understand better how this whole thing hangs together. And I can also change slightly the voltage of the sources, and just by doing so, I get also more reactive power supplied by these sources. If I want, I can also go and look at the phasors of the system. So this is now the phasor diagram. And what you see here now is the contribution from the slack bus. The slack bus has 0 voltage angle and 200 kV, and the other buses are what you can see here and here, and you see also the corresponding power input at these other buses. So this is what I wanted to demonstrate here. You can do it manually, so you learn about the whole system. So cordial congratulations if you managed so far. If you want to repeat the exercise or learn about power system, I strongly recommend to go to this software here. It's an online software. You do not have to download anything. You can just go there and play around with elements, with networks you built yourself.